So now that we've looked at ionic substances and we've looked at covalent substances, molecules, in this lesson we're going to look at what happens when the ionic world interacts with the molecular world, the covalent world, so to speak. And that's going to require us to get introduced to a new type of intermolecular force called the ion-dipole force. We're also going to look at, well, why do some ionic substances and covalent substances dissolve in water but others don't? Because this is probably the most classic example of how ionic and polar covalent substances interact. Okay, so we started this unit saying that hydrogen bonding was the strongest type of intermolecular force, dipole-dipole was second, and London dispersion forces were the weakest. Well, it turns out we weren't quite truthful about that. It turns out there is a force that's stronger than hydrogen bonding, and that is the ion-dipole force. And if you look at what kind of force that is, it makes it pretty obvious as to why. If you think about the types of forces that these other ones are, they're all sort of forces that involve partially positive and partially negative forces. Every single one of them, including dipole-dipole interactions, but even London dispersion forces, we're talking about those temporary dipoles where the positive and negatives aren't permanent, but they're still partial charges. Now you can imagine if you were a water molecule here and you saw another water molecule, well, a hydrogen bond really is the most polar type of dipole-dipole interaction. And so there's a strong attraction from that lone pair to this dipole on the other molecule. But imagine if you were a water molecule and you could interact, you could see something that wasn't sort of partially positive like this hydrogen is, but flat out positive like a sodium ion, or flat out negative like a chloride ion. Well, as a water molecule, you'd be extremely attracted to those. And that's what an ion dipole force is. It's the force between an ion, like sodium or chloride ion, and a polar molecule. It's called that because, well, in dipole-dipole interactions, you have a polar molecule that has a separation of charge. It creates a dipole, and it's attracted to another dipole. Well, here we have a dipole, a polar molecule, attracted to an ion. So chemists, being simple people, called it an ion-dipole interaction. So why is it stronger? Because there's a full-blown positive or negative charge that polar molecule is attracted to. So it's going to be stronger. So an ion-dipole intermolecular force is created whenever any kind of ion interacts with a polar covalent molecule. And as you can imagine, every single time a salt dissolves in water, this is going to happen. So it's very, very common. And this ion-dipole is really strong for the reasons we just talked about. You can see it's actually stronger than a hydrogen bond. These interactions can also occur with nonpolar molecules. In the same way you get an induced dipole when you have electrons moving back and forth in a London dispersion force, you can imagine that if this positive ion was near something that was nonpolar, the electrons in that nonpolar molecule would be attracted towards the positive charge, and you would sort of get an induced dipole there. Now, I don't really use this term ion-induced dipole, but you may see it in other places. We're pretty much going to focus on just ion-dipole interactions where you have a polar molecule attracted to an ion. Okay, so how does this actually happen? Well, when a salt dissolves in water, it's going to require us to break up the lattice that's going on here. And in order to induce these positive and negative charges to separate from each other, after all, they're very attracted to each other, right? They're going to need to have something to be attracted to out here. Imagine yourself being this negative charge. You're going to want to be stuck to that positive cation. So there must be something about these waters that's attractive. And you can imagine what that is. It's the positive hydrogens that will orient themselves towards the negative charge. And if you look down here, the positive charge, it's the oxygen, the negative oxygen, the partially negative oxygen, that orients itself towards the positive ion. Now, water is not fully charged, and so often it takes many water molecules to surround each ion in order to give it enough stabilization of charge that it will be happy to have left its positive or negative ion back at the beginning. So ion-dipole forces happen whenever a soluble ionic compound dissolves. Every single time this is going to happen, and it takes multiple water molecules to create what's called a hydration sphere. And look at the orientation as we just talked about there. It depends whether it's the positive water ion, then you'll get those negative oxygens oriented towards it, or if it's the negative one, you'll get the positive hydrogens oriented towards it. And water is a pretty amazing substance. That's why it can solvate or dissolve positive and negative ions, because it can just orient itself properly. But this leaves us with a question. Why do some ionic solids dissolve, like sodium chloride, potassium bromide, lithium carbonate? Well, all the 1As, right? All of those dissolve according to our solubility rules. But these compounds don't. And they're ionic too. It seems like their ions could be solvated as well. Well, that gets down to a little understanding of energy. Whenever you break something apart, for instance, you break apart this lattice, which would be required to dissolve, right? It requires you to put energy in. It always takes energy to rip apart positive and negative ions. They don't want to do it, so you're going to have to put energy in. If it takes a lot of energy to do that, then this salt isn't going to be likely to dissolve. Let me give you an example. You know that, well, potassium bromide being a 1A element, it dissolves pretty well. And look how much lower its lattice energy is than silver bromide, which is an insoluble salt. So if it has a lot of lattice energy, these ions aren't going to want to separate, and therefore it's going to be hard to get this to dissolve. But that can't be the only factor, because if you look in here, you'll see other salts that, like for instance calcium fluoride, is soluble. It does dissolve despite the fact it has a pretty big lattice energy. So having a big lattice energy will definitely hinder dissolution. But the second factor is, well, if you have to put energy in to break the lattice apart, when you reform these intermolecular forces, energy will be released. So those ion-dipole interactions that are newly formed will always release energy. And if you get a lot of energy back, that can make up for having to put in a lot of energy in the beginning. Think about it this way. If you're a business, you have to put in a lot of money to build a product, and then you get money back when you sell it. Well, it doesn't really matter how much it costs you to build that product if you get a lot back in the end. I like to think of iPhones as an example. I mean, think about iPhones. They got to be pretty expensive to build, right? But Apple gets paid a lot when people buy them. So therefore, it's okay that if they're a fair amount more expensive than maybe other phones. So it's these two factors that are going to matter so much. It's a balance between the two that determines if a salt will dissolve. You got to be more in the green than you are in the red in order to get a salt to dissolve. So more energy must be released than put in for a salt to dissolve. Ooh, I wish I'd put a D on that. So let's look at an example here. If I were to say, well, why does lead chloride, why is it insoluble in water? Well, there are a lot of reasons behind it, but really what we're about to do here is we're about to foreshadow to thermodynamics, which is our next unit this year. So some of these terms may be new to you. Like you may have never heard that putting energy in is called an endothermic process. Ooh, let me go back. An endothermic process, and getting energy released is an exothermic process. You know how when we were doing gas laws and we got to the end and we were seeing the difference between an ideal and a real gas, that if we had known something about intermolecular forces, that would have been easier to understand, and we just had to be patient until we got to this unit? Well, this is the same thing. Energy is the focus of our next unit, but these two terms we're going to introduce here. Okay, so why is lead chloride insoluble in water? Well, the energy required to break the lattice of lead chloride must be high or low compared to the energy you get back when those ions get solvated. Well, because it doesn't dissolve, the energy required to break the lattice of lead chloride must require more energy than you get back when the ions solvate at the end. Otherwise, it would dissolve, right? Let's try another one. Well, sodium nitrate, being that it has a 1A element in it and all nitrates dissolve, is very, very, very soluble in water. Why? So what I want you to do is I want you to write a short paragraph describing the process of sodium nitrate dissolving. And be sure to label each step as exo or endothermic. which part of it is exo or endothermic. Give specific names to the forces that are broken in the beginning and formed at the end. And then I want you to state whether the energy being released is greater than or less than the energy being supplied. All right, so here's the answer I came up with. I said, well, because sodium nitrate dissolves well in water, the endothermic lattice energy supplied to break the ions, endothermic meaning put energy in, you almost don't, you really don't need endothermic and energy supplied. They mean the same thing, but we want to use the term. The endothermic lattice energy supplied to break the ions apart must be less than the amount of energy you get returned at the end when the sodium ions and nitrate ions form an ion dipole, because we wanted to say what it was, right? The ion dipole force that's formed between those two. It must be true you get more energy back than you put in, because otherwise this thing wouldn't dissolve. Just like a business that had to spend more money than it got back when it sold, it wouldn't be in business. So here, because it dissolves, you've got to be getting a lot of energy back at the end. But this process works for other things too. Like, watch this. Let's just start with this. Which do you think would dissolve better? CH3OH, methanol, or ethane? And I'm talking about in water. Well, if you were guessing methanol, I think you're right. I mean, look at it. It can hydrogen bond in water. But that's not what I want to focus on. And skip this. Clearly, I forgot to cut that out. That's not what I want to focus on. Let's focus on ethane. Why does ethane dissolve poorly? So what I want you to do is, because ethane is covalent, it has intermolecular forces with things, I want you to describe the process of ethane dissolving. Because it dissolves poorly, well, let's start with this. Discuss which intermolecular forces must be broken to separate the molecules of pure ethane to get them ready to dissolve, and the molecules of pure water to get them ready to accept the ethane. So which intermolecular forces would you have to break between pure ethane molecules and pure water molecules? And then I want you to discuss which intermolecular forces would be formed between an ethane and a water molecule. And then, of course, based on the fact that it dissolves poorly, well, must the energy being supplied to break the intermolecular forces be greater or less than the energy that gets returned? Okay, here's what I came up with. Well, to get ethane to dissolve, it's clearly going to have to leave its old ethane buddies. Well, London dispersion forces must be what breaks into ethane molecules, right? So if an ethane is attracted to another ethane, to get it to dissolve in water, they're going to have to leave each other. See ya. Well, that is a London dispersion force, because these are nonpolar compounds. Well, what about water molecules? Clearly, water molecules are attracted to other water molecules, and to accept the ethane, they have to separate. Well, you're going to have to break a hydrogen bond. And of course, any compound that can hydrogen bond also has dipole-dipole and London dispersion forces. So those are what need to be broken. Now, which intermolecular forces would need to be formed between an ethane, let's do it right here, an ethane and a water? Well, there is going to be an intermolecular force. Could these two hydrogen bond? No, this has no lone pairs to accept the OH over here. Can't do that. Could they do dipole-dipole interactions? Well, in order to do that, this would have to be polar, and that would have to be polar. But this is nonpolar. Nonpolar. So it cannot form a dipole. You're not going to get a dipole-dipole interaction. So the only interaction it can do is a London dispersion force. So the only intermolecular force that can form between ethane and water are London dispersion forces. Now, which of these two must be greater? The energy supplied in the endothermic step or the energy released in the exothermic step? Well, the fact that it dissolves poorly tells us we must be putting more energy in than we're getting back out. So the endothermic energy step energy supplied to break the intermolecular forces in pure ethane and water must be greater than the exothermic energy released when the London dispersion forces form. Got to be putting in more than you're getting out if this stuff won't dissolve. Okay, let's try we're going to do one more of these, and then we're going to finish up with a short little just test of what you think. So acetone dissolves quite well. And you see acetone up here in the corner? It dissolves quite well. So what I want you to do is I want you to write a short paragraph and discuss which intermolecular forces must break in pure acetone, which intermolecular forces must form between acetone and water, and where's the balance of energy based on the fact that acetone dissolves quite well in water. Well, here's what I think. Between two acetone molecules, between this one and another one, well, they can't hydrogen bond because there's no OH, right? So I do think these are polar compounds because there's 1, 2, 3 electron groups. I think that this is going to be both. Well, let's talk about two things here at once. I think it's definitely going to be trigonoplanar. The bond angle is going to be 120 degrees. Ooh. If I asked you for the hybridization around this carbon, what would you say? Well, there's 3 directions, so we'd say sp2. There's a sigma bond, a sigma bond, a sigma bond, and a pi bond, right? Okay, anyway, I got distracted. So between, since this thing is, no dipole here, no dipole there, because those are 2 carbons, but you do have a dipole towards the oxygen, it is polar, no doubt about it. So that's why you're going to get dipole-dipole and London dispersion forces between 2 acetone molecules. In water, we know hydrogen bonding, dipole-dipole, London dispersion forces. All right, let's figure out what's going to happen next. If you have an acetone molecule and a water molecule, well, what intermolecular forces will form between those two? Can they hydrogen bond? Yes, even though this couldn't hydrogen bond by itself, it does have a lone pair and an oxygen, which can be attracted to the OH over here. It can hydrogen bond. And of course, if it can hydrogen bond with water, it can do all the rest as well. Now let's figure out which of these two must be larger. Is the endothermic step of adding energy in, is it more or less energy than the exothermic step of getting energy out? Well, acetone dissolves quite well, which tells you you must be getting more energy out than you put in, or else it wouldn't dissolve. So the energy supplied to break the forces in pure acetone and pure water must be less than the energy released as you formed the intermolecular forces between acetone and water. Now, I know this leaves a lot of questions. There's obviously a lot of why behind this. A little bit of it's answered in the intermolecular forces, but a lot of it, you notice, we're thinking about things in terms of energy. And the big takeaway here is it always requires you to put in energy if you break bonds, and you always get energy back if you form them. Okay, one last check here, and really this is an aside, but I just want to see what you think. Which of these do you believe would dissolve best in water? Number 1 or number 2? Well, definitely number 2 is the answer. Why? The reason is because all of these carbons, remember these are carbons with a lot of hydrogens, this is a hydrophobic area. It doesn't like water because it's nonpolar. But you have a nice hydrogen bonding area down here that is hydrophilic. Because it can hydrogen bond, it likes to dissolve in water. Well, this one has the same hydrophobic area, but it's got 2 hydrophilic areas. So it's kind of a balance between the part that doesn't like water and the part that does like water. Let's try another one. Which of these do you believe, let's say A or B, would dissolve better in water? Well, based on what we just learned, the answer would be B. Because it has a small hydrophobic area, a nonpolar area, whereas this one has a much bigger hydrophobic area. So this one doesn't have as much stuff that is sort of afraid of water, and it has a great hydrogen bonding group. So definitely B would dissolve better. Okay, I know that was a long lesson, but it introduced us to ion-dipole forces, which are the strongest or weakest of the forces. Definitely the strongest. And we looked at why do ionic and covalent substances dissolve in water but others don't, from an energy perspective. That you have to put energy in to break bonds, and you get energy back when you form the new forces, and it's the balance between the two that determines if something dissolves.